Welcome everyone to this webinar. My name is Eric Belanger. I'm the president of AGT. So to start with, so thank you everyone to be there with us. We will present you today some new product that we've developed involving self-learning technology, more over low volume, high mix production, and specifically for girders, manufacturer, and cross frames. So first, if you see on your screen, you have a control panel on your right side of the screen. You've got an orange arrow that you can click on if you want to move it outward, so you'll have a better view of the screen. As well, on the bottom of it, you'll see a question icon, so you can click on that and you can write down your question during that presentation. So at the end of the presentation, we will answer the question that will be asked during the webinar. So, yep, thank you all. We'll start now, and I wanted to talk to you first about our environment to start with. So the use of robotic welding technologies has become common among manufacturers today due to numerous benefits. First, robots are becoming more affordable and user-friendly. Second, we see a rapidly declining workforce of skilled workers, specifically welders in the industry. You see all that as well. And experts are saying, and we're believing that as well, that automation is a key element to the future of manufacturing. So technology changed quickly. We've seen a lot of changes in the last years, and we have to embrace these technologies to be more productive and efficient. Let me talk to you about China, just to give you an idea. China buys actually almost 50% of all the robots in the world. And we are talking a lot about reshoring of our production in North America. So we have to know that these Chinese companies are getting more and more involved into robotics, and we have to do that as well. I'll talk about Mexico now. We are from Canada, so we are seeing that Mexican companies are using 10 times more robots than the Canadian companies. And we have to as well take that into consideration, but moreover, skilled workforce. I've talked about that. The American Welding Society is stating that the average age of our welders actually in the field is 55 years old. And by 2020, we will have a labor shortage of almost 300,000 welders in the industry. So we're losing our expertise and we're losing our young people to that field. So we have to take that into consideration as well. Now, that being said, why would you like to put robots on your shop floor? Why would you like to automate? Love would say, I want to reduce my cost. I have quality issues I want to increase. But my belief is mainly we want to get rid of that. We want to get rid of the pain in the ass. We have problems with quality, welders, so on and so forth. So it really is a pain in the butt. So we want to get rid of that. Then, why robotic welding? I'm going to state 5 advantages that we see on robotic welding. Quality, consistency of quality, cycle time as well into the productivity, less work in process, the overall cost of the manufacturing of these parts, labor and safety, and mainly it has to be a part of the company vision. Company that embraces technology and robotic, it's part of the vision of a long-term vision into a company. So we have to believe that these robots can help and know that we need rapid payback on these robotic cells, which it does. Then I want to just AGT at a glance. AGT has been founded in 1992, and we got hundreds of automated and robotic systems installed throughout the world. So we've got 2 locations here in Quebec, Canada. And we got a large network of partners as well. And moreover, we have a passionate, multidisciplinary team, passionate people about the technology, about mainly wanting to help our customer getting better and getting more job and getting more productivity out of their production. And we work in different fields, fabricated structural metal, foundries, forging, boilers, machinery, engine, turbines, and things like that. So we work mainly in the metal industry. Our mission is to help our manufacturing customers successfully adapt robotic in low volume, high mix production environment. So this is something that you'll see as well today. So I thank you all for being here. And what I'll do, I'll let Joe going into the technical aspect of the project, and then you'll see the demo as well. And again, if you have any questions during that, write it down, and we'll see that at the end of the presentation. So thank you, Joe.
Thanks, Eric. So yes, I'm Joe Landry. I'm the project manager for the robotic cell that I'm going to show you today. Before that, I'd like to talk about 3 main points that we talk about just before starting any robotic welding project. We first of all talk about layout or mechanical peripherals that is involved in a project. It can be a fixed robot or a robot on a jib. It can be a robot on a rail or robots on gantry or gantries. In our case, for the robotic welding cell for cross frames, it's going to be a robot on a jib. Secondly, I'd like to talk to you about programming option we need to select to be suitable for the application. So you can go the classical way by teaching the points to the robot with the teach pendant. You can go with offline programming, which involve to have an offline programming software and to have the 3D CAD of your part. And you can also go with AGT developed self-learning technology, which require known or almost no programming time. And the last topic is the compensation. If needed, if you need that, it's because your part are not always in exactly the same spot when you need to weld that. If it's not the case, you will need some sensing. You can have laser touch sensing, and you can also have some wire sensing. You can also need to have seam tracking, and you can also need to have vision to be able to determine what's the location of your seam weld with an image. So what are these things that we're going to weld with the cell? Actually, these are cross frames. They are critical part of the bridges. It's for the bridge stability for steel bridges. You have example on the slide. Most of them are on the X configuration, like you have on that slide, but you also can have some K configuration. The one that is going to be welded later on at the demo is more of that kind that you have on screen. It's important to say that even if the cell was designed for cross frames, you can basically weld anything on that as long as it's within the reach of the robot, of course. Now, what we have here is that we can consider these cross frames as small batch production. Like you see on that image, even if the cross frames may look the same, they are almost all different. So what it means is that you cannot make one program to mass produce like 1,000 of these. You will need, in that case, to maybe make one program for 1 or 2 or 5 or maximum 10 to 20 parts. That means that if you want to automate your production and stay profitable, you really need to find a way to program them quickly. And that's what we did. And I'm going to show you that later on in the presentation. Eric talked about it a little bit earlier, but what are the challenges for the cross-frame fabricator? Well, like he said before, the labor is one. It's harder and harder to find trained welders. And when you get them, they may always leave the company. The other thing is weld quality. We always observe some problem with consistency and also some problem with the specs and standards, which is not the case with the robot. The other thing is floor space. It's very common to see a stack of these cross frames on the floor. It reduces your floor space, and it makes costly work in process. And now here's an overview of the cell I have behind me. Our robotic cell for welding of cross frames. It's made of a long-reach FANUC robot that is ceiling mounted on a jib. That jib is there to be able to have two zones. I'm going to talk to you a little bit after that slide of what are these zones are for. And well, that's it. When you weld on zone 1, you can bring your other part on zone 2 and flip it there too. And when your welding is done, you can rotate the jib and weld the other one. So basically, all that handling and all that flipping part are done hidden time. So the robot basically never stops to weld. So it increases your productivity and your throughput considerably. Let's talk a little bit about the welding. Like I said before, it's not a cell that can weld only cross frames, but there's an example of the welds that can be done. We make horizontal fillet welds, and you could also weld anything on that image, not only the red lines. And that's it, not only X-frames. We'll go ahead with a demo already. So we programmed that sequence with our parametric programming tool. It's already to the robot controller, and so we'll start real soon. If you can see the laser dot, that's the laser touch seam finding. And we'll start to weld right now. So if I talk a little bit about that laser touch seam finding, we already have had that question that is frequently asked in the past. It's how does the robot knows where to weld? It's an excellent question, and actually the answer for that question for the robotic cell we're talking about here is laser touch seam finding. So how does it work? Well, the robot gets coordinates from the program, but it doesn't know exactly where to weld. So to do so, we use laser touch seam finding to precisely determine the weld seam by locating the edges to be welded together. And having these data, the trajectory of the robot is adjusted accordingly. So the main benefits are surface finish and senseless, or even if you have heavy mill scale, it's going to work. It's high speed touch, have high precision. So let's talk about programming a little bit. Like I said in the beginning of the presentation, for this system, we would have used an offline programming software such as Octopus or Robot Master to program the robot. It is what we call offline programming. And it goes like this. You import your CAD to the software, you virtually program the robot and push your program into the robot. Now for the system, we have adopted another strategy, which is our parametric programming tool. It's basically a simple Excel spreadsheet. It's linked to a 2D CAD software that is AutoCAD in our case, and both software are linked through a macro. So what are the benefits, you may ask? First of all, for the system, you only need to have 2D CAD instead of 3D for your parts. But most of all, where it takes an average of 30 to 45 minutes for someone to program the welding of a cross frame, it only takes like 5 to 10 minutes with our solution. And most importantly, it does it much quicker and for a fraction of the price of the standard offline programming software. So it's quicker and it's cheaper. we prepared a video of the programming process with our parametric programming tool. That's what you're going to see at your screen is exactly what have been done to program what you see there. So the first minute are in real time, and the other one are accelerated. So I'm going to describe a little bit what's going on in that video, just for the purpose of that. So first of all, what we're going to see that we remove in the AutoCAD software the unused layers. After that, we come to the spreadsheet. We choose a name for the program and the location to save it on your PC. You select the offset of the part from your table, and then you do your jig location or your jig origin. You do the same for your part to be welded. You need to know your origin, so that's what we've just done there. After that, you choose whether if it's an angle or if it's a T or if it's a channel. In our case, it's a channel that is going to be welded. After that, you just select the thickness of your material and your weld fillet size. And after that, you're ready to select your start and end point for your welds. You already have one size done. And that's pretty much it. It goes in and in for the rest of your parts. Once you have done one part, you generate your sub program, and after that, when all your programs are done, you make the main program, and it's going to be recorded on your PC, ready to be pushed into the robot controller. So in that case, it took like 5 minutes, 30 seconds to generate the whole program for both sides of the part. With our estimation, it should take, depending on the parts, like from 5 to 10 minutes to program it all, which is much better than with any standard offline programming software. So it makes profitable to automate your production, even if you have small batch production. So while the welding continues, what are the benefits for our system? Well, it accepts a wide range of X frames, or even any other part that can be reachable by the robot. You need no programming, actually, you just need to enter some power meters like we saw before. It increases your production volume and throughput. In doing so, it will reduce your production cost. It is reliable because it's a robot. It's easy to operate, and it doesn't require any specialized welding labor.
So thank you, Joe. Eric back again. While we will still see this welding being done in the back, I would like to talk to you about payback. A little bit about what's the payback and how do we work it out. So I said that before. We always need to aim at a 2-year payback maximum. But I'll give you this example here. That example is based on structural steel fabricators. So those numbers are numbers by the Structural Steel Association. So we have, if we take an example of 6,000 tons that you produce per year, it takes 3 hours per ton at $30 an hour. So it makes it about $500,000 of manpower to produce these structural steel members. Now, we don't say that it's going to do 100%. You still have to make a little bit of work by hand, things that are more complex, for example, so you keep that. So we say 1,000 ton, you still do that by hand. Then the rest, 5,000 ton, will be done by robotic cell. So at 0.7 man-hour per ton, same wage, so we are at about $200,000 of cost. That's the differential of manpower cost from a manual to robotic welding. And then if you add that up, every year you could save almost $350,000 just labor. Now you have to add to that a couple of things like consumables, labor issues, quality, work in process. So if you produce more, you'll have your product on the shop floor less time, and saving on job planning as well. So if you add all that, and you can produce more as well. So producing more with the same amount of people means more benefits at the end of the year. So each case has to be analyzed, but these are standard numbers that we see into structural steel assemblies and welding. All right, so we'll still continue seeing that the welding being done at the end, but I thank you all. It's not over yet. We still have the question and answers that we can answer your questions. But first, I'd like to thank you for being here, and specifically thanks our partners for their collaboration. We have Praxair, EZAB, Fabric Robotics among our preferred partners. So thank you all, and I believe that this might be the time for different questions and answer. While this cell is still being, this cross frame is still being welded. I got one here. I'm standing behind the screen now. You won't see me, but I'm looking at the question. What is the maximal reach of the robotic arm? That's an interesting one. This specific robot you're seeing is an M710 20L Fennec robot. That's a long arm. It's got 3 meters of reach, and as you might have seen, it does weaving as well. So it's a very efficient robot, very long reach, and moreover, it's working from a boom. So even the boom it's the 7th axis of the robot, so it's giving you more and more reach. In that specific case, for cross frames, we can do from 18 feet wide to 12 feet, well, it's going to be 18 feet long to 12 feet wide. That's approximately that. We're even looking at putting, for people who use smaller parts, we can like for example an M20 that's got 2 meters reach, so it's going to be a little bit less reach. So, but very often each application requires robots, different reach, different configuration as well, and even different power sources. So we need to use the right equipment and the right configuration for each application. So thanks, that was from Alexander. Thanks, Alexander. Now, Derek is asking, how close does the actual weld seam have to be to the CAD model for the laser to find it? Extremely interesting question. You have tacked these parts by hand with probably measuring tape or jigs, so they might be off by 1/4 of an inch or even more sometimes. It all has to do with what you're seeing now at the back of the screen, the seam finding. So usually you define the precision that you want. So the seam finding might be for 1/2 an inch. So we will try to find the seam within 1/2 of an inch. But if you set it for an inch, it could be an inch away. You have to remember though, so every distance that you add to the seam finding will add a little time to your whole process, because the robots makes a little bit more time to find that seam. So it could be different. And again, you have to know as well, we're talking about parts and precision. The precision of the location of the wire when we weld has to be 1/2 of the diameter of the wire itself. So it has to be very precise with robots. So this is why we need to find the seam, and we need to locate that seam very precisely. James, thanks James. We have, how much parts variation can we handle successfully? If, James, I understand the question well, it might be variation within the tolerances of the part, which I just talked about. So it again, it has to do with the finding of the seam. How far do we go with the seam finding? But it could be. Well, we're not talking about inches because it's going to take you a lot of time to find the seam. But we can go up to half an inch, easily an inch. So up to an inch, it's not a problem in that case. So those were mainly the questions that we had. We could as well discuss about the welding process. It's always different. Either it's a spark that could be done with robot. This particular case here, it's a flux core welding, which is a little bit better with scale and rust on steel. We use a lot of metal core as well and solid wire. So all these processes can be adapted to robotic. And I got another from Derek. In previous application, do you find the individual members still have to be tack welded prior to the robotic welding, or do they have to be restrained in any way? Extremely good one as well. We are looking at different ways of, for example, ease the assembly of these parts. Now, these parts now they have to be pre-tacked. We're looking at, if you look on your web, you can see Vertec. Vertec, they are laser projector, if you have seen that before. So we could, for example, work on two tables, use the Vertec laser projector to actually assemble and fit the parts at the right location. And then you could fit that on one table while the robot is welding on the other table. So in that case, you might need to tack, or you might need to hold down the parts. It's different design and different way to do it. So we can, if we don't tack, yes, we need to restrain the part because of the heat distortion and while welding, so we would need to restrain them down. So you had lots of good questions, my friend. Okay, so, well, we have completed the weld of this cross frames. What I'd like to do then, Dennis, if you can change the screen. We got Dennis, our producer, in the back here. So if you are interested in, well, either that cross-frame welding application or anything else that you think about robotic, you can call us. We're there, and I can help you. This is what I like to do, like going to see you guys and talking about potential ideas and concepts as well. So you got our website on the screen. We got our email as well, and you can phone us directly. So we will be pleased, me and my team, to help you on your projects if you need that. So again, that's it for today. Thank you all. Thank you for attending, and we will be pleased to talk to you again in the time that you'd like. So thank you all.